In this video, we are going to understand the one of digital modulation technique to generate the passcode modulation PCM signal using MATLAB, to plot the passcode modulation PCM signal using MATLAB. In this example, we are going to generate a sine signal, and then from the generated signal we are going to make a sample signal, and then we are going to encode that signal, then decode that signal again. Firstly, we need to close everything and make a time matrix from 0 to 3 seconds with the increment of 0.01. And then we are going to make a sine wave with parameter 2 pi t with frequency 1. Then we are going to make a square wave with the parameter of 2 pi tan t. 10 represents the frequency of the square wave. Next, we are going to set everything below 0 to 0 for the square wave. And then we are going to make the sample signal by dot product the sine wave with the square wave. And then we are going to plot the sine wave with the subplot 211 and name it analog signal. After that, we are going to plot this sample signal with the subplot 212 and name it sample signal. And here it is. But the time is not correct. So what we can do is we are going to add another parameter for the plot, which is the time. And here it is. Much better. Next, we are going to encode and decode the signal. First, we need to set the quantization to 3 with the variable n. And then we are going to set a variable y with u encode, which is uniform encoder, with the parameter s as the input, n as the quantization bits, and 1. And then we are going to set a variable r with u decode, which is uniform decoder, with the input signal, which is the encoded signal, which is y, and then the quantization bit and 1. And then we are going to plot these two signals, and here it is, the encoded and decoded signal. Finally, we are going to plot the square signal, and here it is. But as we can see, it is not pretty. So what we can do is we can limit the axis by using the function axis, and we are going to limit the x-axis from 0 to 3 and the y-axis from negative 0.25 to 1.25. And here it is, much better. Next, in this example, we are going to see the effect with and without compending, which is compressing and expanding the passcode modulation signal. So first, we need to clear everything, close everything, and then make a time matrix from 0 to 3 with the increment of 0.01, and make the analog signal, which is the sine wave with parameter 2 pi t with the frequency 1. Next, we are going to set a variable c with the function compend. The parameter is the input signal, which is x, the mu value is 255, and the maximum value of message signal is 1, and mu compressor. And then we are going to encode the compressed signal by set a variable e and function u encode, the input signal c, and the quantization bit to 3. And then we are going to decode the encoded signal by using function u decode, the input signal, which is the encoded signal, which is e, and the quantization bits. Next, we are going to expand the decoded signal by set a variable o and function compend again, the input signal, which is d, the decoded signal, the mu value to 255, and the maximum message signal is 1, and mu expander. And then we are going to plot the analog signal and compended signal and the received signal using compending. And here it is. And again, the time is not correct, so we can add the parameter t in the plot. Next, we are going to see by encoding the input signal by using the function u encode and decode the encoded signal again, and then plot this signal. And here it is, the received signal without compending. Next, we are going to generate the analog signal with 2 kHz frequency and the quantization bits from 3 to 8 and 16 with compending and without compending. But first, we need to change the analog signal frequency from 1 to 2000 by changing the parameter of the sine wave with 2 pi 2000 t. And here it is. As we can see, the figure is not correct because there is not enough plot for the sine wave. So what we can do is we can even more decrease the increment to 0.00001, and this will take some time to run. And here we go, we can zoom in and we get the signal. But instead of zooming in, what we can do is we can use the function axis again. We can limit the x-axis from 0 to 0.001 and the y-axis from negative 1.25 to 1.25. And here is the figure. But this is for 3 bits, so we can change the 3 bit to 8 bit. And this is the figure for 8 bit without compending and using compending. And we can change the variable n from 8 to 16 for the 16 bits. And here it is, perfect. From this, we can calculate the signal to quantization noise ratio (SQNR) by using the formula 10 times log 3 times 2 to the power of n, then to the power of 2, and represents the number of quantization bits. We can also create this pulse code modulation signal technique in Simulink by simply following the MATLAB coding. Just convert the function from MATLAB into block diagram in Simulink. Pretty straightforward.
In question 3 is given task to use Simulink for example 1. Then open the Simulink. Click the library and browse the signal generator as analog signal. Set the amplitude to 1. Then browse the pulse generator as square signals. Set the amplitude to 1. For the signal generator, set the frequency to 1 and unit is Hertz. For the pulse generator, set the period is to 1/10, which is 1 over frequency. Frequency is 10. And pulse width to 50. Click the library and browse the dot product. Then connect the signal generator and pulse generator to the dot product. After that, browse the scope and set the input to 2. Then connect the input to the dot product as sample signal and signal generator as analog signal. Double click the scope and run to see the waveform of analog signal and sample signal. Set the simulation stop time to 3 to show the waveform in 3 cycles. The sample signal waveform peak is spike and not good. To change it, click the model configuration parameters and click the data import or export. Then go to the additional parameters, set the RIFA'IN factor to 250. Run it again, the sample signal will look good. Browse the uniform encoder. Then change the input scope to 1 and connect the uniform encoder between the dot product and scope. For the uniform encoder, set the P to 1, set the bit to 3 and set the output type to signed integer. Then run. Browse the uniform decoder and connect the encoder and scope. Set the P to 1 and set the bit to 3. Then run. Add another scope, set the input to 1 and connect the pulse generator. Then run. Square signal waveform will show.
So next, I will presenting you how to produce the output sine wave of the second example using Simulink. At first, drop the signal generator blocks and set the value of amplitude to 1. Next, drop the uniform encoder and decoder and also the scope with 2 inputs and connect all the blocks as shown. Next, open the blocks parameter of signal generator and set the unit into Hertz and set the frequency to 1. For the encoder and decoder parameter block, set 3 bit for both. Finally, run the blocks. So this is the result of output sine wave without using compending of 3 bits. By using compending, we need to add 2 more blocks for the compending parts, which is MU, low compressor and expander. For the compressor and expander blocks parameter, set the MU value to 255 and peak signal magnitude to 1. and run the block. So this is the result of output sine wave using compending of 3 bits. Next, we are going to change the frequency from 1 Hz to 2 kHz. By changing the frequency of 1 Hz to kHz, basically we need to zoom the graph. So to get the result without zooming, changing the time base from 3 to 0.001. So let's proceed for 8-bit without compending of 2 kHz. First, changing parameters of uniform encoder and decoder to 8 bits, run the block. So this is the result of output sine wave without compending of 8 bits of 2 kHz. Next, 16 bits without compending of 2 kHz. Repeat the step by changing parameter of uniform encoder and decoder to 16 bits and run the block. So this is the result, output sine wave without compending of 16 bits. Next, we will doing 8-bit by using compending. Add 2 more blocks for the compending parts, which MU lob, compressor and expander. Set the MU value of 255 and peak signal magnitude to 1, run the block. So this is the result of output sine wave of compending of 8 bits. Next, 16-bit with compending. Repeat the step by changing parameter of uniform encoder and decoder to 16 bits and run the blocks. So this is the result of output sine wave with compending of 16 bits.